First thing that you have on the start of the page is this equation here for percent composition. So in order to find percent, we always take the part that we are interested in over the whole. So for example, if I wanted to know what percent of carbon is present in this compound, I would take the molar mass of those two carbons and divide that by the molar mass of my entire compound, and then multiply by 100%. You also have this table here, which is showing you several molecules, their molecular formula, and some percent composition data. So the first question asks us to confirm that these two numbers are correct. So let's go ahead and take a look at that. So I need to find the molar mass of C2H2. So I've got two carbons. The mass of carbon is 12.011, and I need to add that to 2 times the mass of hydrogen. So I got those masses from the periodic table. So this gives me 26.038 grams per mole. This is a molar mass. Carbon is just going to be 2 times the 12.011 number, which is going to give us 24.022 grams per mole. So in order to find the percent composition of carbon, we're going to take the mass of the carbon in the compound, which we found in B, and divide that by the mass of the entire compound. And then we need to multiply that by 100%. So when I solve that, I get 92.26%. So now we want to find the percent composition of hydrogen. So there's two ways we could do this. We could take the mass of hydrogen and divide that by the mass of the entire compound. Or we could simply subtract from 100. So we know that this compound is just carbon and hydrogen. So if we subtract out the carbon, we'll get the percentage of hydrogen. But either way that you use, you'll get the same answer, 7.74%. So does that match what we had in the table? Yes. Okay, so the next couple of questions, we're going to look at filling in this data table here. So let's get the molecular formulas. So the first one that I have to fill in is benzene here. So we're just going to count the number of carbons. So this is just going to be C6H6. And I just went through and counted how many of each type of atom were present. This next one is going to be C4H8. Notice that that's the same as the one above. And then this one is going to be C8H16. So what we want to do now is fill in these percents for carbon and hydrogen for benzene. So I'm going to take 6 times the mass of carbon and divide that by the mass of the entire compound. So when I do that and solve here, multiply everything by 100, it gives me 92.26. So these first two have the same percent composition, even though they're different formulas. They're different molecular formulas. So how could we get, say, this hydrogen percentage here? Well, once again, we can just subtract from 100, and we can get that percent for the hydrogen. So that gives me 14.37. Now, just like with benzene and ethyne, these three have different formulas, but their ratio is the same. So C4H8, well, this guy is going to be 85.63 and 14.37. And this guy down here also has that same ratio, so it's going to have the same percent. So question 2 was to fill in those formulas and compositions. Could we find the percent composition for hydrogen without using the equation? So basically, how did we get this guy right here? So all that we needed to do was subtract from 100. And that works because we only have 2 elements in this compound. So whatever isn't carbon must be hydrogen. Agree or disagree? Compounds with the same percents will have the same formulas. So if we look at these two, those all have the same percents, but they have different formulas. So we're going to disagree here. And our support, our explanation for that, is C2H2 and C6H6 have different formulas, but they have the same percents. The molecule 2-hexene has the molecular formula of C2H12. So without doing any calculations, what is the percent composition for hydrogen in this molecule? So C6H12 is, we can simplify this to CH2. So for every 1 carbon, we have 2 hydrogens. So this is going to have the same percent for hydrogen as my other compounds in the table that had that same ratio. Question 6 says to fill in the empirical formula of each of the molecules in table 1. So our empirical formula is going to be the simplest ratio of elements in a compound. So we can simplify ethyne. We've got C2H2. We can just simplify that to CH. Same thing with benzene. Cyclobutane, 2-butene, and 1-octene all have a 1:2 ratio. So 4:8 or 8:16, but either way, that's a 1:2 ratio. So the empirical formula is the simplest ratio. The molecular formula is a multiple of that, twice or 6 times or whatever. So how do we find an empirical formula if we're just given percents? So this problem walks you through what the steps are. So we have a molecule that has only nitrogen and oxygen, and it is found to be 36.8% nitrogen. So that means that the rest must be our oxygen. So that's going to be 63.2% oxygen. So what we're going to do is we're going to assume that we have 100 grams of this compound. If we have 100 grams of this compound, 36.8% of them are nitrogen. So that would mean that we have 36.8 grams of nitrogen in this sample. Grams of oxygen would be 63.2. So the next step that we want to do is convert both of these numbers into moles. So I'm just going to start with both of these over 1. Now we just want to go from grams to moles, which we can do in one step. So 1 mole of nitrogen has a molar mass of 14.007 grams. And 1 mole of oxygen has a molar mass of 15.999 grams. So I'm going to go ahead and solve to get my answer here. And I'm going to get 2.627 moles of nitrogen. And I'm going to get 3.950 moles of oxygen. So what I want to do now is figure out what the ratio of nitrogen to oxygen is. So I'm going to divide both of these by the smallest number that I just got. So I'm going to divide by this number. So we're just trying to see how many times nitrogen goes into oxygen, which is going to give us a ratio here. So when we solve, this is obviously going to give us 1. And this gives us 1.5. Now, we can't have 1.5 atoms of oxygen. We either have 1 or 2. They come in whole numbers. So I'm going to need to do something to both of these numbers so that they are both whole numbers. So what I'm going to do is multiply these both by 2. And that's fine as long as you multiply everything by 2, because it's still going to be the same ratio. We got that there was 1 nitrogen for every 1.5 oxygens. When we double that to get rid of the fraction, we get N2O3. So that's my empirical formula for this compound. Okay, let's go ahead and try another one here. So a dry cleaning fluid is found to be 18% carbon, 2.27% hydrogen, and the rest chlorine. We want to get this empirical formula. So we're again just going to assume that we have 100 grams of the compound. So that means that I have 18.00 grams of carbon, 2.27 grams of hydrogen, and 79.73 grams of chlorine. So I want to convert all of these from grams to moles. So I need to put grams on bottom to cancel, and moles on top. That's what we're trying to solve for. So I'm going to go ahead and look up these molar masses and then do my division here. So for carbon, we're going to get 12.011. That's per mole. So mathematically here, I'm going to need to do 18 divided by 12.011. And this gives us 1.498. I recommend that you at least write out 3 decimal places whenever you're doing this. Otherwise, you might not get predictable numbers like we're looking for here. So I'm going to put moles carbon. 1 mole of hydrogen is 1.008 grams. So I'm going to go ahead and do my math here. And this gives me 2.252 moles of hydrogen. And for this last one, I need the molar mass of chlorine. So 1 mole of chlorine is 35.45 grams. So whenever I solve that, I get 2.249 moles. So I'm going to want to take the smallest number and divide everything by that. So we do that because we're trying to see if we have 1 carbon atom, how many of the other atoms are we going to have? So this is going to give us 1. Whenever I do this math, this gives me 1.50. And then whenever I do this math, I'm going to get a very similar number because it's basically the same thing. Now, once again, we can't have fractions here. So I'm going to take everything, and if I want to get rid of 0.5, I can double it. So I'm going to double everything. And this is going to give me 2 carbons, 3 hydrogens, and 3 chlorines. So my formula is C2H3Cl3. Let's take a look at another one. So in this one, you're not given percents, you're just given grams. So we don't need to do that step where we assume 100 grams and change the percents into grams. We can just start with the grams that we are given. So we have 13.5 grams of calcium over 1, 10.8 grams of oxygen over 1, and 0.675 grams of hydrogen over 1. So first thing I want to do is change everything from grams into moles. So grams of oxygen into moles of oxygen. Grams of hydrogen into moles of hydrogen. So I'm going to need to look up some molar masses here. 1 mole of calcium weighs 40.078 grams. So that's just coming from the periodic table. 1 mole of oxygen is 15.999 grams. And 1 mole of hydrogen is 1.008 grams. So whenever we solve here, we're going to get moles of each of these compounds. So we're going to get 0.337 here, and that's moles of calcium. 10.8 divided by 15.999 is going to give us 0.675 moles of oxygen. And we can go ahead and do hydrogen here, which is going to give me 0.669 moles of hydrogen. So now I want to divide all of these by my smallest number here. And this one's going to give me 0.5. This is going to give me something very close to 1. And this is going to give us 1. So it's safe to round 1.008 to 1, but we can't round 0.5 to 1. So I'm going to go ahead and double. And so this will give me a ratio of 1 calcium for every 2 oxygens and 2 hydrogens. So that's going to give me CaO2H2. Or if you recognize that this is an ionic compound here, that's just hydroxide. So a better formula would be this guy right here. But I would accept either answer as correct. So now let's talk about molecular formula. So the empirical formulas always give us the simplest ratio. But that doesn't necessarily represent the actual number of atoms in a molecule or a compound. It just represents that ratio. So the molecular formula could be the same as the empirical formula. So for example, for water, the empirical formula is H2O, and the molecular formula is also H2O. Or it could be a multiple of the empirical formula. So if my empirical formula is CH3, A molecular formula could be C2H6 or C3H9. Any of those are possible. So, the empirical formula of a compound is NO2. Its molecular mass is 92 grams per mole. So to solve these types of problems, we need to find the molar mass of NO2. So I've got one nitrogen, and that has a mass of 14.007. And I'm going to add that to the mass of 2 oxygen atoms. So I'm just getting those numbers from the periodic table. So I'm going to do 15.999 times 2 and add to that the 14.007. And this is going to give us 46.005 grams per mole. Now, we want to know how many times does NO2 go into the molecular mass. So I'm going to take my molecular mass, which is 92 grams per mole, and divide that by my empirical mass. So when we solve this, we end up with 2. So I'm going to need to multiply the subscripts in this formula by 2. So I'm going to get N2O4. Okay, so the empirical formula of a compound is CH2. So we need to get this molar mass. So that's going to be the mass of 1 carbon plus the mass of 2 hydrogens. So whenever I go ahead and add this together, we get 14.027. So now I want to take my molecular mass, which is 70 grams per mole, and divide this by my molar mass, which is 14.027 grams per mole. So when I do that math, the answer that I get is 4.99, which we can safely round to 5. So what that means is that I'm going to have to take my empirical formula and multiply it by 5, and I get C5H10. Okay, so this last question, we're going to do it all. We're going to get the empirical formula and the molecular formula. So this compound is 40% carbon. So we're going to assume that we have 40 grams of carbon. Then we have 6.7 grams of hydrogen over 1 and 53.5 grams of oxygen over 1. So I'm going to go ahead and convert all of these from grams into moles. So grams of hydrogen into moles of hydrogen, and grams of oxygen into moles of oxygen. So 1 mole of carbon weighs 12.011 grams. That's just from the periodic table. 1 mole of hydrogen is 1.008 grams, and 1 mole of oxygen is 15.999 grams. So I'm going to go ahead and solve and get my answer in moles for all 3 of these elements here. So this is going to give me 3.330. 6.7 divided by 1.008 gives me 6.647. And this last one here, 53.5 divided by 15.999, I'm going to get 3.343. So just like last time, I'm going to divide all of these by the smallest number. We're just trying to see the ratio of these elements. So then once I go ahead and solve here, So that's obviously going to be 1. This next one, 6.647 divided by 3.330, is going to give us something very, very close to 2. And then this last one here is going to give us something very close to 1. So the answer that I get here is 1.004. So these are all safe to round. So we're just going to round this to 2, and we're going to round this to 1. So that means that my empirical formula is CH2O. Now CH2O, we've got a carbon, we've got 2 hydrogens, and we've got this 1 oxygen. So the molar mass of my empirical formula is going to be 30.026. So we need to see how many times that goes into my molecular mass here. So once I do this division, it's going to be something very close to 2. So I get 1.998. So I'm just going to round that to 2. So that means that my molecular formula is twice my empirical formula, C2.